Whenever you feel an earthquake or see a volcano erupting on the news, it's a pretty dramatic reminder, right? It tells us that the ground we're standing on isn't nearly as solid as we think. Today, we're going to pull back the curtain on these massive, super slow-moving forces that are constantly rearranging the face of our planet. So, let's dig in. So, next time you look at a world map, just really look at it. Have you ever noticed how the coast of West Africa just seems to, well, nestle perfectly into the east coast of South America? For centuries, this was just a weird little observation people made. But it turned out to be the very first clue to an idea that would completely revolutionize how we see our world. Then, in 1912, this German scientist, Alfred Wegener, finally put the pieces together, literally. He didn't just see the puzzle-like fit. He actually backed it up with evidence, things like matching fossils and identical rock formations found on continents that are now thousands of miles apart, separated by oceans. He proposed this wild idea that the continents weren't fixed in place, but were actually drifting. I mean, for its time, this was a totally radical, almost unbelievable concept. And this is a look at Wegener's big idea. He believed that about 200 million years ago, all the land on Earth was one single supercontinent he named Pangaea. As you can see here, over millions and millions of years, this enormous landmass started to crack, fracture, and drift apart, a process that is, believe it or not, still shaping our world today. But here's the thing. Wegener's theory had this one giant, gaping hole in it. He could see all the evidence that the continents had moved, but he just couldn't explain how. I mean, think about it. What kind of engine could possibly be powerful enough to push a landmass the size of Africa or Asia? The scientific community was completely stumped, and because he didn't have that answer, his incredible idea was pretty much dismissed. Well, decades later, technology finally caught up with Wegener's idea, and that massive mystery was finally solved. The answer came in the form of a new, much more complete theory, the theory of plate tectonics. This, right here, was the missing piece of the puzzle that Wegener was looking for. And here's the key breakthrough. It turns out Earth's crust isn't one solid shell at all. It's actually a jigsaw puzzle of these enormous slabs we call tectonic plates. These plates carry everything, both the continents and the ocean floors, and they're all just kind of floating on this sea of hot, molten rock deep below. Now, not all plates are created equal. We've basically got two main types. The thick, less dense continental plates, that's the land we live on, and then the thinner but much denser oceanic plates that make up the ocean floor. And this difference in density, that is absolutely the key to understanding all the dramatic stuff that happens when these plates meet. And here it is. This is the engine Wegener was looking for, deep inside the Earth's mantle. These massive convection currents are churning away like a giant slow-motion pot of boiling water. Hotter, less dense magma rises up, spreads out under the plates, and pushes them apart. Then it cools, gets denser, and sinks back down, pulling the plates along with it. This incredibly slow but unbelievably powerful cycle is the unstoppable force that is literally moving our world. Okay, so we've got these plates, and they're constantly on the move. But what actually happens when they run into each other or pull away from each other? Well, the results are some of the most epic and powerful geological events you can imagine. All right, first up, we've got what's called divergent movement. This is what happens when those convection currents pull two plates away from each other. As they separate, this gap is created, and magma from below just rises up to fill the space. And this process is literally creating brand new crust. Out in the oceans, this forms what we call mid-ocean ridges. But on land, it can create these huge rift valleys, like the Great Rift Valley in Africa, which is actually tearing the continent apart. The Red Sea? Yeah, it was formed the exact same way, as two continental plates just pulled away from each other. So if plates are pulling apart in some places, it only makes sense that they must be crashing together in others, right? This is what we call convergent movement, and this is where some of the most spectacular features on our planet are born. Let's just break down what happens when these plates collide. As you can see here, what happens totally depends on what kind of plates are involved. When two oceanic plates meet, one usually slides or subducts under the other, and that forms volcanic islands like Japan. When two continents crash head-on, the crust just has nowhere to go but up, creating absolutely massive mountain ranges like the Himalayas. And finally, when an oceanic and a continental plate meet, that denser oceanic plate always slides underneath, pushing up coastal mountains like the Andes. And finally, we've got transform movement. In this case, the plates aren't colliding or separating. Instead, they're just grinding past each other horizontally. Just imagine two huge pieces of sandpaper rubbing against each other. That's the idea. So this sideways motion creates these really long cracks in the crust that we call faults. The most famous example, of course, is the San Andreas Fault out in California. As these two plates slide past each other, an absolutely immense amount of stress builds up all along these fault lines. And that's the real key here. Whether the plates are pulling apart, crashing together, or sliding past, their movement is almost never smooth. The friction is just incredible, and all that energy gets stored up in the rock, kind of like a compressed spring, just waiting. And this brings us to a really critical point. As this quote highlights, these earth-shaking events aren't random at all. When you actually map out the world's earthquakes and volcanoes, you're not seeing chaos. You're actually seeing a crystal-clear pattern that perfectly outlines the edges of the Earth's tectonic plates. So when all that stored-up energy is suddenly released, bam! It triggers an earthquake, which can cause devastating tsunamis and landslides. These plate boundaries are also the spots where magma can find a path to the surface, erupting as volcanoes that build new mountains and islands like Hawaii. And while these internal forces are the main shapers of our world, sometimes the surface gets a radical makeover from the outside, like when a meteorite strikes and carves out a massive impact crater. But you know, all of this crushing, melting, and violent reshaping of the Earth's surface, it isn't just destructive. It's also incredibly creative. It's the very process that forges the building blocks of our planet. And that brings us to minerals. To be a mineral, a substance has to tick a few boxes. It has to be natural, solid, and inorganic. But the most crucial part is that it has to have a repeating, ordered internal arrangement of atoms. That's what we call a crystalline structure. This is a great way to see that key difference. Halite, which is just common table salt, has a perfect little cubic crystal structure. So, yep, it's a true mineral. Opal, on the other hand, is gorgeous, but it doesn't have that internal crystalline order. So scientists call it a mineraloid. It's all about that internal pattern. You see, all those geological processes are exactly how minerals are formed, whether it's magma cooling slowly deep underground, allowing huge crystals to grow, or superheated water dissolving elements and then redepositing them in veins. They are the source of the metals, fuels, and materials our entire civilization is built on. But the catch is, they're non-renewable. They take millions of years to form. And that really leaves us with a final crucial question to think about. Our restless Earth has spent eons creating these incredible resources. So as we continue to build our future, the great challenge is going to be managing these geological gifts responsibly. What choices are we going to make to ensure they're around for generations to come?